Hi class, it's Dr. Lindner. In this video, we're going to be talking about chemistry. And chemistry is not the most interesting topic, I would admit, as a student to want to cover, but it is important and it's essential. Why? Why is understanding chemistry, learning about bonds and learning about elements and learning about proteins and carbs and fats, like why is the basics of inorganic and organic chemistry important? Because remember, chemicals and chemistry comes together to make cells, and the cells come together to make tissues. And in a cell, if we just look at just a given cell with a nucleus, this membrane, the cell membrane, is made up of proteins, carbs, and fats, which means that we're going to have carbons and hydrogens and oxygens and nitrogens embedded in here, and they're all held together by bonds. So that's kind of like the big picture, right? And then the human structure of the human body, we need those chemistry. We need proteins. We need amino acids, right? We need muscle mass. We need bones. We need protein. We need protein to be neurotransmitters to help our neurology. We need fats to line a lot of the receptors. We need carbohydrates for energy production. So it's kind of like, the big picture, but we got to get to some of the intrinsics and make sure that you know some of these basics. So chemistry, it's the science of structure and interactions of matter. Okay, well, what's matter? Matter is anything that has mass and it's going to take up space. Okay, what's mass? Mass is the amount of matter that a subject contains. Whereas weight is the force of gravity that's acting on the mass. Okay, just some basic terms. Now, matter can exist in three different forms: solid, liquid, and gas. And all forms of matter are composed as chemical elements. Well, what do we mean by elements? Well, elements are the substances that can't be split into smaller or simpler substances. And there's about 92 elements in nature, and 26 of them occur in the human body. And they're typically represented by chemical symbols that are either the first letter or the first two letters. Like C is carbon, O is oxygen, H is hydrogen, N is nitrogen. But Na, we got two letters. Na comes from the word natrine, and Na is sodium. That's an important element. We know that NaCl, which is sodium chloride, that's salt. We have that in our body. It's a very, very important electrolyte. Super important. And sodium is really important for our cells. If this is a cell and this is a nucleus, sodium is always rushing into the cell, and we have potassium that's trying to exit the cell. As one's coming in, one is leaving through the cell membrane. Sodium and potassium. Potassium is the symbol K. Sodium rushes in and potassium leaves. The four elements that make up about 96% of the human body is COHN, right? COHN. Carbon, oxygen, hydrogen, and nitrogen. And there are some trace elements, and they're present in small amounts. But just because they're in small amounts, like 4%, right, the remaining, it's small, but that's things like copper and selenium and zinc And these are really, really important. I got to meet the gentleman who discovered zinc a few years ago. I had the pleasure, he was nominated for the American Nutrition Association, the ANA. They gave him a Lifetime Achievement Award. This guy discovered zinc. He lived, I think, to the age of 93 or 94, but he discovered zinc as an essential mineral for humans. He didn't discover zinc, he discovered it as essential for humans. And he traveled to Egypt back in the 60s and found a population of people that were very short stature. They had stunted growth and they were eating clay and dirt. And when they tested them all, they were all zinc deficient. And when he gave zinc in their diet, all of a sudden they started to grow tremendously. So there are growth factors associated with zinc. They're all important. And I just want to show you how zinc and copper are needed, and even manganese. These are all trace minerals. I just want to show you that if we look at a cell, and that's the nucleus, this cell membrane has two layers to it, right? The cell wall has two layers, 1, 2. And that's what they're showing here, 1, 2. So this is the cell membrane, okay? And inside of the cell, this is the intracellular fluid. Out here is extracellular fluid. The other name for intracellular fluid is either cytoplasm or they call it the cytosol. Cytosol or cytoplasm. Now, here is the mitochondria. And the mitochondria is making ATP. And the mitochondria, as it's making ATP, it can give off and create oxidation. Remember, I said oxidation is bad. So we need antioxidants. And what helps to protect the mitochondria is this antioxidant that's called manganese. Mn stands for manganese. And the SOD stands for superoxide, right? Oxidation, superoxide dismutase. So it's superoxide dismutase. That's SOD. Superoxide dismutase. Anything that ends in ACE is an enzyme. Anything that ends in OS is a sugar. Anything that ends in ACE is an enzyme. And anything that ends in OGen, OGEN, means it's inactive. So if it was like glucose, sucrose, lactose, anything with OS is a sugar. Anything with ACE, like catalase, dismutase, these are enzymes. So manganese, superoxide dismutase, protects the mitochondria against oxidation. You've got UV light coming in that hits the body and can create damage and can damage stuff within the cytosol or the cytoplasm. So we have copper, zinc, superoxide dismutase. So manganese superoxide dismutase is going to protect what? It's going to protect the mitochondria. And copper zinc superoxide dismutase is going to protect the cytosol or the cytoplasm. So these are like antioxidants. They protect the cell. They protect the organelles. So zinc, copper, manganese, these trace minerals are important to help protect us even at the cellular level against oxidation. How do we quench oxidation? Antioxidants. And that's what these are. These are antioxidants. They act as antioxidants. No different than vitamin C or glutathione or NAC. These are all things that are antioxidants. So elements, let's go back to this just for 1 second. Since I'm talking about antioxidants, and we mentioned earlier about vitamin C being an antioxidant, right? When you bite into an apple and you see that it rusts, that's oxidation. And if you put vitamin C on the bit part of the apple, how it protects it against oxidation because it's an antioxidant. The most powerful antioxidant to humans is called glutathione. This is the most powerful antioxidants, and we make it. Humans make it. And the reason why vitamin C is so important is that it helps to recycle glutathione. So think of glutathione as like a bulletproof vest. And oxidants are bullets hitting the bulletproof vest. And vitamin C goes to the bulletproof vest and just pulls out the bullets and says, okay, bulletproof vest, you can keep working. So oxidants try to damage glutathione, and vitamin C helps to clean it all up and puts it back to action to help protect us. But it's amazing because our human body can make it, but we need amino acids for that. We need 3 very important amino acids. One of them is called glycine. One of them is called glutamine. So you got glycine, glutamine, and the third is called cysteine. This one may ring a bell to people because during COVID, a lot of people were using a supplement called NAC, which is N-acetylcysteine, because glycine and glutamine in our diet is not hard to get. It's quite common, but cysteine is the weak link in our diet. So you can substitute it with something called NAC, N-acetylcysteine. A lot of people into heavy, high-intensity training supplement with it, very good at reducing fevers, but essential to helping complete these 3 ingredients so your body can make glutathione. That's the most powerful antioxidant for humans. When you're not feeling well, if you get COVID, if you got the flu, one of the key things is not just vitamin C. You want to try and get glutathione into your system, and what a world of a difference it makes. Okay, the elements are given symbols, right? So O is for oxygen, and C is for carbon, H is for hydrogen, and N is for nitrogen. These are going to make up about 96% of the human body, just those 4 combined. Now, this shows us the major elements that makes up about 96%, oxygen, carbon, hydrogen, and nitrogen. And it's like, oh God, why do we got to know these things? Why are they important? Well, what's the significance of them? Why do we need oxygen? Well, it's a major part of water and a main organic molecule. So when we talk about organic molecules, they're all going to have oxygen. And we need oxygen to make ATP. Remember the mitochondria of the cell? We got oxygen coming in so that we can make ATP, and the byproduct of that is going to be CO2, which is carbon dioxide that you exhale. So oxygen is important. Carbon, very important. It's the backbone, chain, and ring of all organic molecules. So whether we're looking at carbohydrates, proteins, and fats, we're going to see a long carbon chain like this. That's what it means when it says backbone chain. And then next to each of these, we're going to have bonds. There's going to be hydrogens attached to these on both sides. Hydrogens. Okay? And this is a structure. Structure determines function. Hydrogen, oh, there it is. You stole my thunder here, right? It's involved with water because we know water is H2O, meaning you have 2 hydrogens and 1 oxygen. and it's found in most organic molecules. And it helps to make body fluids more acidic. That's really, really important. The more hydrogen, let's say this is a beaker of water. If you have water in here and you start dumping in hydrogens, if you got lots of H's in here, lots of hydrogens, what's that going to do to the pH scale? 7 is in the middle. So if you start out and the pH is 7, but you start dumping in hydrogen into that water, you're going to drive the pH down this way because acids are here, bases are here, this side. So the more hydrogens, the more acidic. Nitrogens are involved in all proteins and nucleic acids, right? So Cohen is very important. And then you got these, trace elements: calcium, phosphorus, potassium, sodium, chlorine, magnesium, iron. Okay. And yes, you have to know these abbreviations because they do show up on the test. What is K? Potassium. What's Na? Sodium. What is Mg? Magnesium. Fe? Iron. So you need to know what these stand for, what they're used for. Calcium is important not just for your bones, not just for your teeth, but without calcium, you can't clot. We need calcium for clotting, and we need calcium to make muscles contract. And we need calcium to release other hormones. Now, calcium is so very important, and that's why you have two major organs or glands in the body, the thyroid and the parathyroid, are designed to keep calcium in balance. Whenever you look on your blood work, the range for this is pretty tight. It's only 9 to 11 for calcium. So it's either 9, 10, or 11. And your body uses the thyroid and parathyroid to keep calcium levels in check. Too much of it isn't too good. Too little of it is no good. So calcium, not just good for bones, not just for bones and teeth. Without it, you can't clot. Without it, you can't stimulate hormone production. Calcium is needed for muscle contraction and many other things. Nerve impulses as well. Phosphorus, well, that's the P in ATP. ATP is adenosine triphosphate. So all that means is that you have adenosine, not with one phosphate, that would be adenosine monophosphate, not with 2 phosphates, that would be adenosine diphosphate, but 3 bonds to phosphate, which is adenosine triphosphate. That's energy. With 3, it's ATP. With 2 of them, it's ADP. And with 1 of them, it's AMP. Adenosine monophosphate, adenosine diphosphate, and 3, adenosine triphosphate. So when you think of phosphorus or phosphates, we think of energy. We think of ATP. But it's also needed for bone and teeth. Potassium and sodium, both of these are important. Potassium is the most plentiful cation, but it's the most plentiful cation intracellularly, meaning inside the cell. When we look at sodium, Na, it's the most plentiful cation extracellularly. So remember in a picture earlier, I drew a cell with a nucleus, and I said sodium is out here and potassium is here. But there's lots of sodium out here. There's lots of potassium in here. And things always want to move from where there's a higher concentration to where there's a lesser concentration. So sodium wants to go from extracellular to intra, and potassium is the most abundant intracellularly. It wants to go from higher concentration to lesser. That's how things move, how they flow. Okay. Both sodium and potassium, they're both needed to generate action potentials. When you hear that term action potential, what I want you to think of automatically is like nerve impulses, nerve flow, nerve conduction. An action potential is needed to create a nerve stimulation. Think of it that way. And we need sodium and potassium to do that. Now, sodium and potassium, these are both cations, which means that these are positively charged. And the way you can remember that is in the word cation, the T looks like a plus sign, compared to anion has more N's for negative. So anions are negative. So if we look at chlorine, chlorine is the most plentiful anion. They're negatively charged particles. Where is chlorine? Extracellular. Is that a surprise? No, because we have salt outside. We have sodium and chlorine. Sodium, chlorine is salt. So they are grouped together. They are found extracellular. Okay. Let's see, what else? Magnesium. Magnesium is involved in like, I don't know, 500 different enzyme reactions. Magnesium is one of the most deficient minerals of humans. And if you knew how important it was, you'd be supplementing it or making sure you have foods rich in magnesium. It's involved in 300 or 500 different enzyme reactions. It's a really important relaxant. Like, think about when women go through the time of month when your monthly bill is coming and you have cramps because the uterus is contracting. Typically, you crave something. And most women typically crave what during that time of month? Chocolate. Chocolate, chocolate, chocolate. Want to have chocolate. Why? Because chocolate is high in magnesium. And magnesium relaxes muscle. So it relaxes the smooth muscle of the uterus. And it helps to ease the cramps. Pretty neat. Magnesium can also help lower blood pressure because it relaxes the smooth muscle around blood vessels. Iron. Well, what happens if someone's iron deficient? If they're iron deficient, then they can't make energy, can they? So iron is very important because it's affiliated with your blood, with hemoglobin. It's the oxygen carrying protein. Oxygen doesn't travel by itself throughout the body because it'll oxidize everything. It needs to bind to iron. Iron is what carries oxygen around. So if you're iron deficient and you can't carry oxygen into the mitochondria, then you can't produce enough ATP or energy, so you're fatigued. So do you see why these are important? These are all related to function. Just to give you an idea of the ratio of things, carbon, oxygen, hydrogen, and nitrogen, that's how much total human mass is made up of that. And then, you know, the other elements, the trace elements and those lesser elements make up the other 4%. But just because this piece of the pie is so small, my goodness, look at what this small piece of the pie does. So very, very important. Okay, I'm going to pause there. When we come back, we'll get into some of these atoms.